In this video, we're converting complex numbers into polar form and Euler form. Same numbers, different address system. Here's the idea before any formulas. This dot is 3 plus 4i. There are two ways to describe where that dot is. The first one is a grid reference. Go 3 across, 4 up. That's Cartesian form, and that's what we did last video. The second is a bearing and a distance. Go 5 units out at an angle of 0.927 radians. That's polar form. Both describe the same dot. Neither is more correct than the other. But some jobs are painful in one and trivial in the other, which is the whole reason to be able to switch. So, two quantities. The modulus, written with vertical bars around z, is the distance from the origin. And that's just Pythagoras. Root of a squared plus b squared. The argument, written argz, is the angle round from the positive real axis, measured anticlockwise. And there are 3 ways to write it. R bracket cos theta plus I sine theta. That's polar form written out in full. Cis is an abbreviation of exactly that. C-I-S. Cosine, I sine. So r cis theta. And Euler form is r e to the I theta, which looks like it came from nowhere, but behaves beautifully, as you'll see at the end. All 3 of those are the same thing. Now the thing that costs the most marks in this topic. You'll want to say the argument is arctan of b over a, and that is not always true. Your calculator's arctan only ever returns an angle between minus 90 degrees and plus 90 degrees, which means it physically cannot tell the difference between a point in the second quadrant and a point in the fourth. It will hand you a confident wrong answer. So sketch the point first, every single time. Then check that the angle you got is actually pointing into the right quadrant. Example 1. Write 3 plus 4i in polar form. Modulus first. Root of 3 squared plus 4 squared. Root 25. 5. Now the argument. Arctan of 4 over 3. 0.927 radians. And the point is in the first quadrant, up and to the right, so the calculator value is fine as it stands. 5 cis 0.927. Or 5e to the 0.927i. Example 2. Write 1 plus I in polar form. Modulus. Root of 1 plus 1. Root 2. Argument. Arctan of 1 over 1. Arctan of 1 is pi over 4. First quadrant again, so no adjustment needed. Root 2. Cis pi over 4. And keep it exact. Root 2 and pi over 4. Not 1.414 and not 0.785, unless the question asks for decimals. Example 3. And this is the trap. Live. Write minus 1 plus I in polar form. Modulus is the same as last time. Root of 1 plus 1. Root 2. Now the argument. Arctan of 1 over minus 1. That's arctan of minus 1. And the calculator says minus pi over 4. So put that on the diagram. Minus pi over 4 points down and to the right, into the fourth quadrant. But minus 1 plus I is up and to the left, second quadrant. The calculator is wrong. Fix it by adding pi. Minus pi over 4 plus pi is 3 pi over 4. So the answer is root 2 cis 3 pi over 4. And check it. Root 2 times cosine of 3 pi over 4 is minus 1. Root 2 times sine of 3 pi over 4 is 1. That's the point we started with. The calculator's answer would have given you plus 1 minus I, which is a completely different number. Example 4. Now the other direction. Write 4 cis 2 pi over 3 in the form a plus bi. The real part is 4 cosine 2 pi over 3. Cosines of 2 pi over 3 is minus a half. So 4 times minus a half is minus 2. The imaginary part is 4 sine 2 pi over 3. Sine of 2 pi over 3 is root 3 over 2. So 4 times that is 2 root 3. Minus 2 plus 2 root 3i. About minus 2 plus 3.46i. And notice, this direction never has the trap. Going from polar to Cartesian is always safe. Last one. And this is why Euler form is worth the trouble. Multiply 2e to the I pi over 6 by 3e to the I pi over 3. In Cartesian, this would be a full expansion. In Euler form, it's just index laws. Multiply the fronts. 2 times 3 is 6. Add the powers. Pi over 6 plus pi over 3. Common denominator 6. Pi over 6 plus 2 pi over 6. 3 pi over 6, which is pi over 2. So 6e to the I pi over 2. And cis of pi over 2 is just I. So the answer is 6i. One line. And that is the entire subject of the next video. Now the calculator check. Every calculator you're allowed converts between rectangular and polar directly. Usually a pole and rec pair of buttons, or a complex mode conversion. Use it on every single conversion, because it gets the quadrant right, and you might not have. So, modulus is the distance, argument is the angle, and always sketch before you trust an arctan. Next video is what polar form is actually for. Multiplying and dividing complex numbers in one line instead of 4.